Okay, thank you very much. And so let's see, we are here, and let me move full screen. So let's do a little bit of the software demonstration. So you can find all the all the notebooks over there. I'll briefly skim through it, but the whole idea is, if you need it, later on you can just start looking at the code and modify it for what you want. So what we have over here is this goodie library. If you didn't install it, you can maybe install, or you just follow what Greg said, and it should work. So what we are going to do right now, I think I have a better picture over here. So we are looking at the standard triangulation of a torus, where the thing on the left-hand side. So we actually glue this thing together with that thing. This way we are getting a cylinder, but we also glue the top and the bottom of the cylinder together, and this is how we are getting a torus. So by far this is not a minimal triangulation of a torus, but this is a triangulation. And who knows what are the homology group of the torus? Homology group, or the Betty numbers of the torus. 1 to 1. So that's what we are expecting to get. And then if we go back to the software, it's over here. I try to put the torus. But what you are doing, you are just putting a list of maximal simplices into the appropriate data structure for you. So you are starting from 2 simplices. It will generate 1 and 0 simplices kind of automatically as soon as I run this cell. So you don't need to bother, you just need to include goodie. So let me start from the beginning. Now it created a simplex tree, a simplex of dimension 2. We are actually writing down the dimensionality. We can take a look at the number of simplices, and indeed we have 9 0 simplices, which are, we need to count the vertices over here because they are being repeated over there. So indeed there are 9 vertices. There are 9 times 2, which I think is 18 faces, and this is what we see over there. And you can do the math and calculate the edges. But I can tell you there are 27. And tell me. Yep. That's correct. So for instance, 0, 1, 8, over here, if you look at the first one, I think this is this triangle over here. And you are just going over all the triangles. So there should be all 9 times 2 and all 18 triangles. No. Okay, so I'll be speaking a little bit about this, what goodie is mostly for persistent homology. And over here we are using Z2. So we do not introduce the orientation. And that in that particular example, okay? I won't be throwing sweets that far because I can hit someone. Okay? So we have the insert function, and then we can compute just a standard persistence and get the Betty numbers. And indeed, this is what we get. So this is the 0th second Betty number. And of course, when you have triangulation of pretty much anything, you can just adopt this code by inserting the top dimensional simplices, and it will do the calculation for you. And there are ways to add filtrations, etc., etc. So that's the most basic example of just inputting a triangulation into the piece of code. And this is, of course, the illustration how we are getting a torus from gluing the sides accordingly. So if we glue 2 sides, we get the cylinder, and then we glue one side to the other to get a torus. So that's pretty standard. Okay. So what I want to present right now is actually what is happening under the hood of the computations at the moment when I hit this button. So to the computations of the persistent homology, what is indeed happening under the hood. For that purpose, there is this idea of a filtration sticking together for quite some time. So I want to explain it on a simple example. It won't be something similar to this. So we start from a simplicial complex, and I enumerated all the 4 vertices from 1 to 4, all the edges based on the vertices. So there is edge 1, 1, 3, 2, 4, 1, 2, and 3, 4. And if you notice, I put those numbers next to the edges. So the lowest number is at the edge 1, 3. And this is the first edge that appears in the matrix, and the second one is 2, 4. And then there is 1, 2, and 3, 4. So those numbers over here is 5, 7, 6, and 8. Those are the filtration values of the edges. And the last thing that comes, it's the value of this cube. Yeah, so we are looking right now at the cubical complex. I mean, practically speaking, no, it's just the same as a simplicial. It's just a little bit different geometry of the simple elements or regulation Lego building blocks you are using to build your complex. By the way, still you can ask questions and you will get the stuff. So what do I mean by this boundary matrix? So if you look at the edge 1, 3, it has the vertex number 1 and the vertex number 3 in the boundary, and this is what is denoted over here by those non-zero entries. Everything else should be 0, but of course I'm not putting all the zeros. Over here, it's very much like the philosophy of the sparse matrix. So the edge 2, 4 has vertex number 2, well as a vertex number 4 in the boundary, and the whole cube 2, 3, 4, 1, 2, 3, 4 has all the edges in the boundary, and therefore we have those ones. There are ones and not minus ones because we are working over Z2. As I mentioned, we do not look at the orientation at the moment. So what I want to do is I want to get from this matrix into a reduced matrix, just kind of in an echelon form. So I'll do some sort of Gaussian elimination, and it will come in the next slides, step by step, to move from here into here. And the echelon form is, so if you look at the, so first of all, the vertices has empty boundary, and therefore there are those empty columns. But if you look at the lowest non-zero entry of every column in the reduced matrix, which is this element over here, this element, or that element, they are unique. So there is no other lowest non-zero entry in the same row as, so there can be at most one lowest non-zero entry in every row in the reduced matrix, and this is what we are going to achieve by actually doing the version of a Gaussian elimination or a version of a Gaussian reduction. So this is our working example, and I want to guide you step by step, explaining what the code is actually doing. So we have 4 vertices, A, B, C, D. We have 5 edges. This edge, this edge, this edge, that edge, that edge, and the red numbers tells you the order in which they are coming in the matrix, and then we have one 2-dimensional cell, which is the ABC triangle. So that's the part of the boundary matrix. I'm not showing you the boundary of the vertices because they are, by definition, that there is nothing. As I said, there is nothing. So what we are going to do is actually we'll be looking at the columns from left to right and checking some condition. So I'm looking at the first column, and the condition I am checking is as follows. So I'm looking at the lowest non-zero entry in a given column, and I'm looking if somewhere to the left from this, in the row corresponding to this lowest non-zero entry, there is a lowest non-zero entry of some previous column. Okay, so just bear with me, because there is nothing before this condition is automatically satisfied for the first column. So let's go for the second. So this is the lowest non-zero entry of the column AC. I'm looking to the left while there is nothing non-zero. So condition is satisfied. Let me move over here. So when I'm having a column BC, the lowest non-zero entry of this column is the same as the lowest non-zero entry of the previous column. This is what we called in this algorithm a collision. And we want to get rid of the collision. Remember, we want to have it on the echelon form. So that thing cannot happen because those two columns have lowest non-zero entry in the same row in the row C. So in order to deal with it, we are taking the column BC and replace it with BC plus AC. And I am doing the addition modulo 2. So we are working over the field coefficients. So 1 plus 1 will be 0, 0 plus 1 will be 1, and 1 plus 0 will be 0. So that's the effect of the addition. And now I still need to check the same condition, right? So if the lowest non-zero entry of this new column is unique, and I'm looking to the left, and it's not. Because again, we have a collision with the first column. So we are resolving it in exactly the same way. So actually those two columns are identical. So if I add them modulo 2, I'll get an empty column. Well, there's no lowest non-zero entry, so there is nothing more I need to check. So I can happily move after to the column CD. And I'm checking the same condition. Well, there's nothing non-zero over here. So I can move further. And I see, again, the collision. So the lowest non-zero entry of the column BD is the same as the lowest non-zero entry of the column CD. So I'm making an addition. So 1 plus 1 equals 0, 1 plus 0 equals 1, 0 plus 1 equals 1. And we have another collision between this column and that column. We resolve it in exactly the same way. So 1 plus 1 is 0. We have 1 and 1. And another collision, which is resolved this way. And, I can check the lowest non-zero entry of that column. It's empty. So now the matrix is reduced by essentially using very simple Gaussian elimination. And what I'm claiming is that we can read homology as well as persistent homology from that information. And what we actually did during this resolving of the conflict has very deep meaning when it comes to homology. So let me explain how. So the reduced matrix gives you the persistence intervals. So I need to tell you, okay. So maybe for the persistence intervals, I want to quickly move to this animation. So if you remember, I mentioned about the homology classes. So over here, we are looking at homology classes in dimension 1 homology. And we look for the radius in which we first see the class, and we call it the birth radius. And we look at the radius in which we see the last for the class, which is the death radius. And then persistence of a class is the difference between the death and the birth. It tells us for how large ratio of radii we actually see the middle hole. And of course, the larger the persistence, then the bigger, in a sense, is the class we are looking at. So coming back to the matrix example, is somewhere here. Oopsie. So this is how we can read those persistence intervals, the birth and the death pairs from the matrix. So if the column is 0, it's a birth. Something is created. I'll tell you why in a second. If the column is non-zero, so there is some non-zero element, someone, then it kills a homology class. And let's take a look together again on this reduced example. And this time I put back all the vertices. And remember, when we are moving from left to right, this is how the filtration is progressing. So we really think that this complex is built gradually, step by step. And let's see how the homology is changing. And let's just try to interpret what's happening on this reduced matrix. Okay. So at the very beginning, we have a vertex now A added first. It creates a connected component. We have a vertex B being added, a vertex C being added, and a vertex D being added. They're all empty columns. So this is a creation of homology class. In this case, a class of the dimension equal to the dimension of the cell, which is 0 in this case. So at that moment, as we are here in the filtration, we have 4 homology classes in dimension 0, 4 connected components as you wish. Okay? Let's move to the next one. So there is a non-zero column, and it's a kill. What do I mean by that? Well, I mean that addition of that simplex kills whatever was created at the over here at the column B. So at the column B, we created this connected component, and by adding an edge, we are killing this connected component. So right now, we used to have 4 connected components, and now after addition of this edge, we have 3 connected components. Okay, so that's what a non-zero column is telling us. So once we are adding the column AC, then edge AC, that's another kill, and we can see it geometrically. Again, the connect that used to be a separated connected component, and now is merged with A. And what you can observe over here is something what we also call the Elder rule. So we are always killing the thing that is coming last. So for instance, when the edge AB, we are killing the youngest element in the simplex AB, which is B. So we are, in the other words, we are letting A, who was born earlier, to persist. That's not very humanitarian if you think, but you want the longest connected components to live as long as possible because you want to catch the persistence, the largest possible span of a homology class. And this is how we are doing it. And that's exactly the application of the Elder rule. Very much so over here. So with the addition of the edge AC, we are killing the connected component we just created at the vertex C. And this is what we see geometrically. Okay. Now something interesting happened. So we have this reduced empty column. It's a birth because it is a 0 column. And indeed, we have a creation of a homology class. Well, what dimension? Well, the dimension of the homology class is dimension of this element, which is 1. And indeed, we see a creation of a cycle. And how do you interpret it? Well, the interpretation is pretty easy. So before the reduction, let me move back right here. So before the reduction, we had the boundary of the edge BC. And the fact that we were able to reduce this whole column means that the boundary of the edge BC was possible to generate from the stuff that is already in the complex. So we could generate a chain which is equal to B plus C from what we already had before BC was introduced. So we have already, BC as a boundary. We have added that thing. It means that we really closed the cycle, or we closed the homology class. And that's exactly the interpretation of what is happening over here. And this is precisely the cycle that we are getting. And moreover, if you see over here, we get a cycle representative. So we got a representative chain of this homology class that we created. Okay? Then let's move forward. So when we are adding an HCD, that's a kill, and we are killing whatever was created in the D vertex. And as you see, of course, the number of connected components goes down. Again, the Elder rule applies. And we have a similar story right here. There's an empty column, it's a birth. This time it's a birth of another homology class. We see another cycle. But if you look at the representative, so the representative really is the thing that actually wraps around the whole thing. And we have another kill right here. So addition of this ABC triangle kills whatever was created at BC. So what was created at BC is, where is BC? There it is, right? So we created this cycle in BC, and by adding this element, we killed the cycle. Okay, so in order to get the persistence intervals, the only thing that we need to do is just look at the pairings. So AB have a filtration 5, and it kills the B, which has the filtration value 2. Hence, we have a persistence interval in dimension 0 from 2 to 5. Okay? Look over here. AC, where is it? AC is here. It has a filtration value 6. It kills what was created at C. C has a filtration value 3. Hence, we have a persistence interval from 3 to 6. And the last example is here. So we have CD. CD has, where's CD? Filtration value 8. It kills what was created at D, which is 4. This is this persistence interval. And we have that guy. So ABC has a filtration value 10. And it kills one-dimensional cycle, which was created in BC, excuse me, which has filtration value 7. It's this guy. Well, we are still missing one guy, right? This one. And we are also missing the A. So we did all the pairings. And if the pairing is made, actually the column is used, and there are 2 more columns that we should consider. The first one is the A column. Is responsible for the whole connected component of the simplicial complex. And A appeared at 1 in the filtration, and then it's forever, so we have this infinity. And likewise, we have that column created in BD, which appeared at 9, and in this filtration it wasn't killed, as it's the infinite class. Okay? So, once I run the software for the torus, I only gathered the infinite classes, and this was the one-to-one thing that you notice at the end of the execution. So what happened was actually, started from top-dimensional simplices. All the lower dimensional simplices have been generated. This boundary matrix was created, and then we ran this Gaussian elimination, and the information was read out by the software exactly as we did it over here. So this is what is happening over under the hood. Any questions about that? You want me to go over something? Let's go. Yeah.
If under the hood doesn't letter, you're talking about all the letters, the A, B, C, the how does it.
Okay. So, we started from Vittori's ribs or check complexes. And the typical input is a collection of points, right? So we get a vector of points. They are naturally ordered, right? Because we are working in Python, let's do a proper ordering. So this is the 0th element, first element, second element. So the vertices they have a nickname coming from integers, and the nicknames are essentially the position in the list as you introduce the points. Okay? Okay. I'll try not to kill anybody. Brace yourself. Good job. Both of us. Okay. Where's my pointer? Okay, so any more questions? So the whole persistent homology, blah, blah, blah computations, that's exactly what we are doing. That's essentially a Gaussian elimination, bringing a boundary matrix into an echelon form. So the TDA community spent the last 15 years optimizing this process. Big step forward was to use sparse data structure instead of full matrices. But there are various ways of clearing, so you don't need to do some of the reductions because some elements will clearly be reduced, so we can make them to 0, and it's from geometry. There are many strategies to do it. This is how persistent homologies work. Everybody okay? Nobody wants a sweets. Lunch is coming, I know. That's, okay. So I got a few propaganda slides why persistent homology is nice. So the features we are capturing are the homology classes and their lifespan. And then kind of the construction of Vittori's, this is the Vittori's ribs complex. If we construct the Vittori's ribs complex up to simplicity of dimension 2 or 3, we really don't care what's the embedding dimension of those points. That is an advantage in certain occasions. Persistent homology is based on the homology So some of the transformation that preserve homology don't matter to us. Sometimes it's good, oftentimes it's good. And this is where topology is not as rigid as in geometry. So I can take a point cloud, I can rotate it. Persistent homology will be exactly the same. I can shift my point cloud. Well, persistent homology do not care about that. Useful in many occasions. We'll take a look at a few of them. It's multi-scale. The question, what you see, of course, is a vague question. Somebody wants to answer. There are at least two possible answers to this. What do you see over it? Right? So is it a collection of cycles of relatively small diameter? Or maybe you see the big picture, which is a big cycle composed of those. I mean, all the answers are possible, and I deserve two of them. But that's for me. That's for me as well.
Well, let's say about I think currently we're going to do their full class.
Yeah, let's assume that there are very, very densely sampled points, all right?
Then because you're like me, minus me, I don't agree.
So again?
Like these circles and almost isn't theaters on the Arab within that.
Yeah. No. Like imagine that, you know, those are points. It's just they are so densely sampled that you cannot see that those are separated points. Yeah. Dude, that's a circle. There's a song about turtles my kids like. About turtles. Question, okay? Okay. You don't want this. Okay, I can get you out. Come on. Can you? Yeah. For the demonstration. Tell me.
I did.
I mean, just for fun. Okay, multi-scale. And there's this robustness thing. Right, so when you are doing data science, there's always noise. And you want your characteristic, whatever characteristic data you have. I mean, if you sneeze of your data, you don't want the characteristic to change too much. So let's take a look at what is happening over here. The previous talk, we have the idea of persistence diagrams. So let me briefly discuss what we are looking at. So first thing on the left column, first of all, I sampled very nicely points from unit circle. And I added a little bit of noise over here, but you kind of, still see this Platonic idea of a cycle inside empty space, and then I put more noise. So on the right-hand side, that's the way of encoding those persistence pairs we have over here. So every pair is a pair of number, birth and death. So you die after you are born. So typically the second number is greater than the first one. But let's not do the looper thing, all right? Typically the first number is greater than the second number is greater than the first one. Therefore, you have a collection of points which is above the diagonal. So this is y equals x diagonal. And this point, for instance, the x coordinate represents the birth time, and the y coordinate represents the death time. And that point tells us, okay, we are looking at dimension 1 homology over here. So it tells me that there is a one-dimensional cycle which is born just after 0 radius, and it persists until actually, I really need to start wearing glasses. 1.7, let's say. So there is 1.7 over here. So it's pretty long persistence, right? Let's take a look over here. So that's the perturbed version. We still see this point which kind of sticks away from the diagonal. Now the birth time is around 0.4, and the death time is around 1.4, but it's still considerable persistence. We got a little bit of junk. So for instance, maybe over here, for some short range of radii, we'll see a homology class, but it is created and very, very soon after for just a little larger radius is killed. So that's the noise. And if you ever do a signal processing, we have a signal to noise, and the signal to noise ratio is still pretty good. The same story over here. So the persistence of this dominant point is going down, but I mean, we can still see the signature of a cycle quite clearly. And that's the robustness of the persistent homology. I will state and the wave the stability results in a few seconds, but this is how it works in practice. I think before I state it, I think we should have, that's the robustness thing. So persistent homology is a feature of your data. If your point cloud, you can get this thing which is called a persistence diagram. And then, well, then what? I told you that's something like an average on steroids. Well, what you can do with averages? You can take two populations and compare the averages. Well, in order to compare, we need to have a notion of distance between persistence diagrams. And I'm going to introduce one of them. But what is the other thing we can do? And I'm kind of jumping ahead, and I'll discuss it in details in a second. We can use averages in statistics, machine learning stuff. We'll be speaking how to take persistence diagram and also embed them. So those are the two things. Okay, so imagine that we have two persistence diagrams, which, no, one is marked, so the points of the first diagram are marked in red, then the points of the second diagram are marked in blue. And what you can notice is that I have two red points, and I have many more blue points. And I want to have a matching between one diagram and the other. Of course, if I have a set of two elements, in a set of many more than two elements, there is no bijection if you look at this like this. But in order to actually being able to match persistence diagrams of different cardinality, we can realize that the points on the diagonal, they are something like a virtual particles in quantum physics. A homology class that appears and dies almost immediately. There are points with the birth and the death time equals. So for the sake of this comparison, we imagine that we add, infinitely many points, red points along the diagonal. And right now we have the sets of the same cardinality. So we can match them in a way. And over here, there's a possible way of matching when this red point is matched to this blue point, likewise over here. And the blue points over here are matched to the diagonal, and all the points that are in the diagonal are matched to itself. And I can define a cost of this matching. There are various ways. I can, for instance, look for the longest edge in this matching. It will give me a bottleneck distance. Wait a second. I can look at the longest edge. I'm taking back the last sentence. Or I can sum up the length of those edges. Or maybe I can sum up the squares of the length of the edges and take square root of the sum. And so there are various options. But once I do it, then I can actually look for the matching with the lowest weight among all the possible matchings between those collection of points. And if I'm looking at the maximal shift, so at the longest edge in the matching, and if I take the infimum over all possible matching, I'll get a bottleneck distance between diagrams. If I'm looking at the sum of the length, I will get Wasserstein 1. If I'm looking at the sum of the squares of length and then square root of this, I'll get Wasserstein 2, and you can figure out how to get the p-Wasserstein distance out of it. So that's a metric between persistence diagrams. Questions? Okay. And so remember, over here I introduced some perturbation to the points. So I perturbed x and y coordinate by a random variable sampled from a uniform distribution of a certain. So when I actually do the perturbation, I kept the perturbation under control. So I could just move the point by a certain amount and not more. Same over here, a little larger amount over there. And the persistent stability theorem, which will appear eventually, but it's not here at the moment, tells me that in the bottleneck distance, the maximal amount of shift I did on the point, it will upper bound the bottleneck distance in the persistent homology. So what I want to take a look at is this script, which is called persistent simple point cloud. So we can just go ahead and open it. It's in one of the notebooks. There it is. All right. So again, we can pip install goody. We get all this stuff. And what I'm doing over here is to generate points from a standard parameterization of a unit circle. So I'm generating 100 points from a unit circle, and I can plot it to you. So here they are. And I can construct the ribs complex. So this time I'm taking the maximal radius 1.8. So I'm limiting the radius. I don't want the radius to be too large. Maximal dimension 2, because I'm interested, well, because I know that my points are from the plane. I know that in principle I am expecting connected components and cycles, but no, not voids and higher dimensional homology classes. So that's reasonable. And I'm calling this ribs complex construction computer persistence diagram, which is here. So the 0-dimensional classes are in red, the 1-dimensional classes are in blue. We have the infinite class. You have this 1-dimensional class, which is born quite early. So it's more or less, around 0.1. And it dies about 1.7. And we got, that's a point with high multiplicity. So because I'm actually having a very nice uniform sample, excuse me?
3 points, but
now I have more than 3 points. That's what I'm saying. So the point in the bottom, but wait for it, okay? Give me 30 seconds, and then if I didn't answer, then you ask again. So the spacing is almost the same. So for a very, very small radii, we'll have 100 points, 100 connected components, because this is the number of points I generated right here. But then once we reach the half of the spacing between points, they all became connected. That's why, that point over here, it's really have multiplicity 99, because we are having 99 classes essentially dying together at the same time. Does that answer your question? Good. All right. Okay. So that's a very clean situation. Never happened in data science. Let's put some noise. So what I'm doing over here, as you see, I am adding I am adding a random uniform variable between 0 and epsilon is 0.8. So that's quite a big perturbation, especially because the radius of my cycle is 1. So that's the perturb cycle. Doing the construction again. So you see it's much more noisy. Again, right now, all the points, they are not dying in the same way because they are spaced with different intervals. We get some possible cycles appearing, somewhere in the middle. You can imagine that there are some short-living cycles appearing. But, what's important is, again, the signal-to-noise separation. And we have this guy responsible for a cycle, and of course, the connected component. So that's the robustness part, but we can still compute the bottleneck distance between this diagram and the diagram you have over here. Clearly, they have different cardinality. Well, in dimension 0, they have the same, but in dimension 1, they have very different cardinality this time. So I did the perturbation of the level of 0.8, was it epsilon? So that's, and the bottleneck distance in dimension 0, both in dimension 0 and in dimension 1 will always be bounded by 0.7, and in dimension 0 is close to 0.2. In dimension 1, it's a little bit more than 0.5. So if you want to actually play with it a little bit more, right now I can regenerate the this noisy point cloud with a little lower perturbation. Much cleaner, right? And I'm expecting the bottleneck to be below 0.4. So let's take a look. And indeed, it's below 0.4. So that's kind of experimental verification of stability theorem. Yes. Well, the bottleneck distance, so you are matching points of two diagrams, and you are looking for the longest shift. You are looking for all the possible matchings, and you are looking for the one that minimizes the longest shift that you need to make. Yes, so you have a matching between points in the diagram. Yes. Well, you can see which classes are matched to which. The problem is, if you want to go back to the data, the inverse problem in topology is not that easy. So let me go back to the example we have when we actually did the right here, right? Maybe right here. I mean, you would expect to have two nice classes, which is, this edge plus this edge plus this edge for this hole, this edge plus this edge plus this edge for that hole. If you look at the algebra, this is not what you are getting. The localization problem in homology is kind of ill-posed. So if you want to match topological features of the data set, keep in mind that the generators may be not very far from being optimal. There's a lot of work on trying to make them optimal. I'm happy to discuss it offline or over lunch. But this kind of inverse problem from homology to the data is very tricky. So be careful, right? Okay. I'll try. Oh, Carlos, come on. There's another one for Carlos coming. Watch out. Okay, I didn't kill anybody, and I hope you do to keep it like this. Prego. Okay, so that was the stability illustration in practice. Sure, you also want one, right? Go on.
I was wondering, you pursue your point cloud with uniform non.
That's right. Sure.
So, back in data set, you pursue what kind of noise?
Right.
Because looking at the diagrams, could you tell me if I start a little bit one or the other?
So the answer is I don't know. But I have a question. Why are you asking this question? Because do you want to recognize the type of the noise? Wait for it, okay? Maybe not this lecture, but maybe in the afternoon. But we'll be speaking about recognizing. I shouldn't be integrating, not speaking, apologize. We'll be speaking about recognizing solving goodness of fit problems in the statistics. Which seems to be what you are asking for, right? So yes, we can do something, and we have a tool, we have a statistical test. Just wait for it, all right? Any other questions? Yes?
But should also use the statistic.
We can. We'll get to that. Okay, so if you look at Wasserstein stability, so I'll put them up in, let's say, 20 minutes, maybe half an hour. Depends how we go. In the Wasserstein stability, you don't only have the amount of shift, but also number of syntheses coming into place. So when explaining the stability result, I started from bottleneck because it is the cleanest one, in a sense. But we'll get to Wasserstein. Yes, you can. We could modify the code probably. It's pretty easy. And you get similar conclusion, but it will be kind of one-to-one with the shift, because also there's this factor of the number of syntheses coming into the Wasserstein stability. All right? Make sense? Yes?
Okay. Like,
Oh, wait a second. Okay, so you are asking if topology. So if you have a correlated noise, so are you asking if topology TDA can detect correlation between variables? Yes, it can. I'm not sure if this is the most efficient way of Pearson correlation will want to do a better job, but in principle, yes, you can see the signature if they are correlated or not. And if you can imagine, if you have uncorrelated variables, let's say V1 and V2, if they're uncorrelated, they will be all over the place. So there will be a lot of room for, cycles, but at the other hand, so this is not correlated. If they are correlated, they will be much smaller.
let's say it's correlated. Doctors knowledge.
And that's a great question, higher order correlation. I thought about it. And the question is, yes, if you tell me which subsets, I can tell you if they are correlated or not. Again, we are looking at asking the questions about all possible subsets, and that's very painful computationally. So I don't know if that's the case, if there is a smarter way, but I'm not aware of a smarter way, off the top of my head at the moment. Does that answer your question? Yeah, anybody else? Okay, where are we? We are here, and I want to be here. And there's a grocery coming to my wife. Okay, so that was persistent homology, and it is stable with respect to some type of noise. So it needs on our data, we shift a little bit the points, and the result wasn't too bad. However, if we do this or that, that's much worse. And you call it somehow salt and pepper noise. So we kind of added at some points sampled from a uniform distribution. Well, why is it bad? Well, it is bad because during persistent homology, we are starting to growing balls. And if we are just growing balls over here, by the point they get over there, they need to grow by roughly the diameter of that cycle. But if we put those points in the interior, they will be growing by itself, and this cycle gets killed much, much sooner. So, this story serves as a motivation for multidimensional persistent homology. I'm not going to get into this because the number of practical tools is limited essentially to Rivet at the moment. But the idea is, well, in persistent homology, they say, okay, you should take the radius, but there is something different between, those points over here and the points over there. Namely, this point lives in the high density region. And we can measure the density by looking at the distance to my second neighbor, right? So if I'm standing over here, say that you're my first neighbor and maybe Jesus is my second neighbor, so we are kind of 3 meters apart. Okay, I'm in the low density region, but you guys in between, you are in much higher density region because your second neighbor maybe, 1 meter away, maybe 1.5 meter away. So that's how, they ensure that in the second filtration parameter, those points are actually appear much later, and therefore this big cycle is not killed immediately. However, unfortunately, due to a deep problem in representation theory, multidimensional persistence is not available as a practical tool at the moment, not to the extent we would wish to. So we need to be aware that persistent homology is not stable with respect to this type of addition of, I call it salt and pepper quote-unquote noise. I'll provide you a partial solution. So it's not tragic. We have something. Just bear with me for a second. So the story is, we presented it for the point clouds, but the use is much, much, much larger. So we also look at the pixel voxel data, and I will show some examples. Time series, I will mention one example, but we'll come back to this piece of music, the violin phrase that I was torturing you at the beginning of the lecture, and correlation similarity measures. So if you have all this type of data, you can use persistent homology let me briefly mention a few projects. So for cubical homology, we are actually part, and then in my discovery center of a consortium looking at the signature of some bone degradation diseases like osteoporosis. So we are getting this type of CT scan, micro CT scan, they're clinical. So if you are ever tested for osteoporosis, and I hope you're not, what they typically would do right now would be to measure the density of your bone. So it, they take your age, look at the density of your bone, they take your gender, then say, okay, people of your gender and that age are supposed to have a density with this range. If you are with that range, you're good. If you are above, you are kind of a Wolverine type guy. If you are below, then let's better have some treatment. That's roughly how it works. What we are having over here is we want to look at the structure of the bone, and actually seems to correlate even better with the resistivity property or the risk of a major fraction within certain horizon. And for this, we are using cubical complexes, also implemented in GODI. So I won't be going, it's just another representation of spaces. Speaking about simple cubical regular CW complexes, we'll also be speaking about regular CW as a Lego blocks. So you have a Lego blocks of different shapes, and you are allowed to build stuff out of it. And that's, just another type of Lego blocks. And you can have everything else looks the same, you just need to attach them properly. Okay, so I have an example from a cubical complex. The example is kind of the distance to measure type example. So let me maybe explain to you what we are going to do. So here we have a function from a square, or from -2 to 2 to real number. It's defined as a distance to a unit circle. So what do we have? Is this square and a unit circle somewhere here? And at every point, we are looking at the distance. So the length of that edge, the length of this edge, is the value of the function from at this point. So what will be if you look at this function, it will have a minimum, actually a 0 value on the cycle, and it will be growing as you go inside. We'll have a local maximum over there and a collection of local maxima over there. So when you're moving away from the cycle, and of course the value is growing. Okay. So what we are going to do, we want to understand the sublevel sets of this function, and we'll do it by dividing this square into a grid of points. At every element of the grid, we'll compute the distance, and then we'll treat it as a cubical complex and compute persistent homology of that cubical complex. All right. So what I need to do is, it's called distance, pH distance from a cycle. So I'm going right here, and there it is. This is pH distance from a cycle. Again, we need to import some stuff. And I'm creating 100 by 100 grid. So there's the grid. So the dark region means the minimum, and you see the local maxima at 0, and also the local maximas at the corners. So that's the function we are looking at. Okay, it's being recorded. Here's the persistence diagram. Okay, so I'm not sharing. But we lost the we lost the connection. Yeah. Yes, sir. That's it. All good? Yeah. Okay. So that's the persistence diagram, and once again, the topology of a cycle. So we have a connected component. Right in here, we have one-dimensional cycle plus a little bit of noise coming from some numerical approximation. Let me just move this guy aside. All right. I don't want to join. Okay, I'm good. I'm just me too. No, I mean, yes, we can do the same for a periodic cubical complexes. So I won't be speaking about the periodic in this case. If you are doing some finite element simulations and you would like to do periodic stuff on the torus, come talk to me. Otherwise, it may be too boring. Time series analysis, we'll be speaking a little bit more about it, so I just want to mention work done by Mérida and Yucatán. So what we are looking at is a S&P 500 index over the last 30 years, more or less. And they introduced some measure of instability of markets, which kind of correlate with, this is 2003, that's 2007, that's 2013, financial crashes. So that there is a lot of potential over there. And I think there's a so I mentioned the bone project we are doing with the consortium of medical doctors, but also looking at the materials with porous structure, there is a lot of potential. So in this work, we actually use the machinery of persistent homology that I mentioned to you. And over here, you can see, so over on the left-hand side, we see geometry of some zeolites. So zeolites are nanoporous materials. So those are the pores in the zeolites, and essentially we are speaking about atom scale. So the diameter of those pores is roughly at the maybe order of 10 diameters of oxygen atom, or something along those lines. So those are very, very atomic scale structures that are being sampled, and the sample points are the blue points. And on the right-hand side, that's another representation which was popular back in the days, developed in Stanford. Right now, people mostly use persistence diagram, but the idea is the same. So you can have a collection of bars, and it's called a barcode. And the X value of the beginning of a bar is the birth. The X value at the end of the bar is death. That's equivalent to persistence diagrams. And using those tools, we are able, let's say, to look for the best possible materials for a given task, or help looking for possible materials and avoiding too many molecular dynamics simulations, which are very expensive. And you want a little bit more of the story, I'll be happy to give it to you. But I want to change the gears. So about persistent homology and multidimensional persistence is a growing field. It's a lot of resources. By the way, I also put the slides online to the folder. So we have the folder, we have everything. You can look at various tutorials. And yeah, I encourage you to talk to me or look at the tutorials. So right now I want to take a step further and still stay within the range of persistent homology. But what we've been speaking about is, the pipeline when we start from data, and we got persistent homology, which is a feature of data. And as I pointed, statistics on steroids. So we have a metric structure. So we can compute persistence diagrams of different collection of points with various Wasserstein or bottleneck metric. But I also want to use it in the setting of statistics and machine learning. And I want to briefly talk a little bit about, that branch. So how to interface it with the standard machine learning tools. Okay, so let's take a look at persistence diagram. It's a collection of points, pair of points, birth and death. Birth is less or equal than death. It may have different sizes, and we saw it on the experiments. It's pretty bad news. Different sizes are not good for machine learning. In order to actually do something, we want to embed them either to a Hilbert or Banach space in order to make the use of standard tools in statistics /ML/AI possible. And, there's a toolbox in Booty. So I won't be torturing you with examples, but you can cook up some of them when you actually have this intermediate stage before you actually embed it into ML or stat. RAI. And I want to discuss a few ways you can actually do this embedding to the spaces. So, question is why? So if you look back in the days, there is a very nice paper, Yuri Milienko and a group of people from Duke. They proved some nice properties of the space of persistence diagrams with Wasserstein distance. It's a complete space, it's a separable space. Some local compactness properties. So there's this concept. You have a space that satisfies those conditions, which they show that space of persistence diagrams with Wasserstein distance satisfies, and you have a fresh mean. So you have a concept of a mean. The concept of a mean is very important because imagine you sample a data from some process with noise, and you want to understand what's the average behavior. In order to do it, typically you are taking an average, hoping that the signal will be amplified and the noise will be brought down by the process of taking average. There's a problem with those fresh means. I mean, they are not unique. So let me tell you what a fresh mean in case of persistence diagrams is. So over here we have two diagrams. One are denoted by the pentagons, and the other one is denoted by squares. So the pentagon diagram contains those 2 points. The square diagram contains those 2 points. And, you can set up the optimal transport plan between one diagram of the other. And then the fresh mean, so the optimal transport we can visualize by the line segments as we did so far. And the fresh mean, we just select for every line, you select the midpoint. And you put, a point of your average diagram in the midpoint. It's very good as long as you have a unique transport plan. Which again, in some non-generic situations, you don't. For instance, over here, you can match vertically or horizontally. If they are organized like this, they are equally well transport plans, and those average objects, they exist, but they are not unique. And that's pretty bad because, when I'm doing some inference, if I have a choice, then, so that's why people started to think around, okay, we cannot do it this way. Can we do it better? And there were a number of attempts. First of all, the attempt was, take a persistence diagram and let's compress it into a number. Maybe you can use this number as our feature. So we can look at the number of non-diagonal points. Very simple, but used in some papers. Sum of the persistence, average persistence entropy, actually kinds of resembles Shannon entropy. So Li is this verb minus def in this case. I think I missed this denote. This symbol. So there are various ways you can take a persistence diagram and convert it into a number and then do the stuff. But of course, the main philosophy of TDA was not to lose information. That's why we are lifting it to a much more complicated space, not to project it down to a single number again. And therefore, a number of vectorization have been also introduced, for instance, as a function. So we can have a Betty curve, and I will explain what it is in a second. Persistent landscapes, or persistent silhouettes are also possibilities. They're all implemented in the software packages, all kind of advantage and disadvantage. So let me briefly mention the persistence Betty curves. So let's imagine that we have a diagram. And over here, actually, the representation of a persistence in terms of the persistence barcodes is better. But so let's take a look at the blue one. So the blue diagram only contains 1 point, which has the birth value 1 and the depth value 3. So that diagram was a single point. So if we look at this persistence bar of 1 and 3, we can associate a step function, which is 1 has the value 1 at this interval, and everything everywhere else have a value 0. So that's the step function corresponding to this diagram. And since there is nothing else, so the persistence Betty curve is just the sum of the step functions for all the points in the diagram of the same dimension. So over here you see this is just this function I draw over here for the blue one. The red one contains a few more, and therefore you have a little bit more complicated step function. But the idea is the same. So you're taking a persistence diagram and it gives you a function. So for a long time, people actually believed that this is not a stable representation, but we are able actually to prove that there is a stability with respect to a Wasserstein distance, in this case, 1 Wasserstein distance. So that's a nice stable representation. You can see so on your data, and they won't change too much. So the global group of people back in the days from Fort Collins, I have Colorado, Henry Adams and co-authors get another idea, which roughly is, when you have a persistence diagram, you can rotate it, but it's kind of a technical one. But then when you have a point, you can just, substitute the point with a small Gaussian kernel. So you put a small Gaussian kernel centered on every of those points. And the points of the higher persistence get larger Gaussian kernels, so with the larger amplitude. Points closer to diagonal, then they get a smaller Gaussian kernels. Then you take the sum of those functions and you get a persistence image. So the sum of the functions, I think we call it somewhere, but then you discretize it on the grid of points and you get a persistence image. There is some more elaborated stability also related to a Wasserstein distance. So those ways are the main ways in which you can take a persistence diagram and obtain a function of some sort, or a collection of functions it represents. And once you have a collection of functions, you can vectorize them, and they serve as a nice input for statistics and machine learning. But that's a necessary step to actually move from this unstructured collection of points into something that is usable. And as I mentioned, it is implemented in this package and many other packages. So, there are a few of them, orders of 10 to 20 vectorization methods available at the moment. The reasonable ones are implemented, and you can just plug and play. I think there's another example of a collection of points, the persistence image. There's another function which is called the persistence silhouette. I don't think I want to go into the details, or a Betty curve. All of them can serve as a vectorizable representation of your data. This is something you put to statistics, machine learning. I won't be going into details, but that's the idea. Any question about this idea? Okay, so I think next time I should put this. I was already disappointed. It just didn't say, okay, tell me. I don't.
Yeah. Yeah. Well,
yeah. So I do not know a general answer. So there was a recent paper by Rocio González Diaz, Vidit Landa, Maria Hosner was also over there. And they tried to compare different vectorization methods on some benchmark data sets. Because I don't think there is a theoretical reason why one of them is better than the other. We don't have it. So what they did was a standard machine learning approach. Machine learning, excuse me for a second. So in machine learning, is a random forest better than SVM classifier, better than cat boost? Well, we don't know. If it was, nobody would use the weaker one. It's very much like with the vectorization methods. It depends on the task at hand. So when you are having a classification, regression, whatever learning problem, The way to go is to try many of them, see which performs best for your data, and just go with it. So what Rocio did, Maria also did, was try to define a nice and consistent data set. And by the way, this is exactly why in machine learning, they have a standard data set on which they are testing stuff. They try to provide a reasonable data set, test various vectorization methods, and then see which performs best. And I don't remember the conclusions. So there wasn't one clear. I mean, for different data sets, different methods had an upper hand. And that's why, so now I remember. This was the conclusion. There wasn't a clear winner. Very much like in machine learning. Okay? Any other question? Yes?
He was great. When they showed that was good. What? Because we have to get down to the ability of but that is what's in the body, when it's bars.
Okay. So, yes, they are stable. And it's pretty easy. I can prove it over here. So look, if we take a persistence diagram and the perturbed version, and we find the optimal matching, then, for instance, it's a matter of simple calculation that if you go, okay, so let's say I will take the Wasserstein distance, so the sum of them are the bottleneck. So if I take the bottleneck, so what can happen if I have a persistence of a pair BD, which is depth minus berth? Well, if I make a perturbation of a P, so let's let P be the bottleneck distance, then, in the worst case scenario, what can happen is I can move by P towards the diagonal, in which case the persistence of each point will decrease by P, right? So that's the worst case I can do. And I am summing up over all the possible points. Let's say the endpoints in the diagram. I get this factor of, so that's the average before, and that's the average after. So that's the average persistence. That's not the average. This is sum of persistence, sum pH before perturbation. And over here I have sum before minus n times P, where P is the bottleneck distance. So I got some minus P plus P, sorry. So I'm looking at the absolute value. So the maximal amount, this sum of the persistence diagrams may be affected is at most by the number of persistent points times the bottleneck distance, and the number of persistence points is bounded by the number of simplices. So, you can cook up easily in the stability proof for most of them. And yes, I would say they're trivially stable. Let's keep it as a folklore knowledge. Nobody actually wrote a paper about that, because it doesn't deserve to be a paper. I'm sorry for being a little bit clumsy, but it's a very simple thing, right? So imagine what could happen in the worst case scenario. The persistence of each point will be increased by P. Nothing worse can happen, and you get this bound, right? Increase or decrease. In the bottleneck for Wasserstein, you can cook up something over lunch. That's essentially how it is, all right? Any other questions? Yes? Uh-huh.
It's helping balance how it does.
Uh-huh.
That's all.
Correct.
There. Another podcast. They take the money in reality on 50 million. Okay, is another world not Topology
Absolutely.
Yeah.
Yeah. I mean, so there is a recent preprint or paper. I'm not sure what's the status. But Sarah Kalisnik and co-authors, they they actually look at the idea of growing balls, but not this way, but kind of, you know, in the ellipse fashion. So you have one preferred axis in which you are growing, and they have some motivation why they have some working example why they want to grow in when they want to prioritize one direction and not the other. So that's kind of what you are saying. We are not looking in the standard topology when our neighborhoods are ball of a fixed radius, but maybe ellipse of a certain aspect ratio. Yes, and people are doing it. So Google Sarah Kalisnik, look at the two recent papers and you should be able to find it. It came on arXiv this year. I don't remember the title of the term on my head, but if you don't find it, tell me and I'll find it for you, okay? Okay, any other question? Okay, here's my kicker. So where are we? Those are the resources again. Frog book, cubical homology book, my arXiv tutorial, YouTube videos, including Geotop, AATRN, and many others. I want to come back to that thing. Right, so I mentioned, okay, you know, persistent homology is stable with respect to one type of perturbation, but not necessarily with all of them. And that's the case. And I mentioned, well, you have this multidimensional persistent homology. However, with all the caveats of non-existence of analogs of persistence intervals, so practically no. But I told you that I promised you that I'll present a partial solution. So before lunch, I want to keep my promise. Before lunch, I want you to remind me. So I'm always doing daddy's joke. Remind me to do one before lunch, okay? Okay, don't be that bad. Don't worry. Other characteristics. So this is one of the first non-trivial topological environments. So probably the first one was about connected components, but I would say Euler noticed, it wasn't Euler. Actually, if you look at the history of mathematics, it was somebody before him. So you notice that if you take a convex polygon and you take the number of vertices, subtract the number of edges, and add the number of faces, you always get 2. That's a manifestation of the fact that every convex polygon has one connected component, 0 one-dimensional cycles, and one generator in dimension 2. So if we look at the Euler number, this is 1 minus 0 plus 1 plus 2. Okay. Again, what he contributed with this work is, first of all, Lego blocks. We already discussed it. So building kind of complicated spaces for simple pieces, but also this invariant, this characteristic which we can generalize. So if we have a general CW simplicial or general CW complex, we can count the number of simple k-dimensional cells multiplied by -1 to the dimension and some overall dimensions. That's the Euler characteristic. Euler Poincare formula relates it to Betti numbers. So we get an alternating sum of the Betti numbers. Why am I mentioning this? Well, first of all, there are a couple of reasons. Depends what drives you. And I think I'm driven by both of them. So first of all, it's something extremely easy to compute. In order to do compute persistent homology, you need to do a little bit of linear algebra that we discussed. You need to do this matrix reduction. But over here, you compute your simplicial cubical CW complex, and you just need to count number of cells in dimension 0, number of cells in dimension 1, and you do this alternating stuff. Extremely easy, very easy to parallelize, very easy to distribute. So if your motivation is computational simplicity, you got it. your motivation is the existence of some results in mathematics. I mean, Euler number has this property that it's kind of, present in many different theorems across mathematics. Riemann-Roch, Gauss-Bonnet, Euler-Poincaré. If you look at the theorems, that there is an Euler number or somewhere over there. It means that actually many people for many years did a lot of work, provide some theoretical background. Maybe important. We'll come back to this. I think you asked me over there about the statistical tests. So this is where we are going to come back to the statistical tests. Okay. So what I'm trying to do, what I'm proposing you to do is, we used to have persistent homology, or which was defined for a filtration on a complex. Instead of looking at persistent homology, for every step of filtration, we can compute the Euler characteristic. As the filtration progresses, the Euler characteristic is evolving, and we are getting this curve. So over here, I have a filtration. Over here, I have the value of the Euler characteristic. Euler characteristic is an integer value function. So, it jumps in between integers. And so over here, what we have is an Euler characteristic of a collection of points, again, roughly sampled from a unit circle. And the balls are growing, filtration is progressing. So once again, what's the Euler characteristic of unit circle? Continuous pink. So let's look at Euler-Poincaré formula. We need beta 0 and beta 1. What's beta 0 of a cycle? 1. What's beta 1? 1. What's the Euler characteristic? 1 minus 1 equals 0. And as you see, that flat region is an evidence that we are dealing with a cycle. This is where it's equals 0. At the beginning, stuff is growing, maybe not everything is connected, but then we have this long flat region when we actually get an evidence we are dealing with a cycle. So let's zoom in version. Stability. So once again, it's something I'm proud of. So there is a folk knowledge that Betty curves and Euler curves are not stable. They are stable. The proof is very easy. So there's a formula. I promise you to show you the formula for the Wasserstein distance. So we are summing over all Berg-depth pairs. We are looking at the Berg-depth pair, and the pair it's in the other diagram it is matched with. You are looking at the distance to the power p, sum to the power 1 over p, and you are taking the infimum over all possible matchings. That's easy. What we have over here is the illustration, very much like the one we did with the software. So we have two collection of points. There is a blue collection of points. Once again, very nice sample of a cycle. And there is an orange collection of points, which is a perturbed version. On the left-hand side, on the right-hand side, we have diagrams. And this line over here, and it indicates the bottleneck matching. The bottleneck matching or the Wasserstein? This is Wasserstein matching because they're actually matched over here. Okay. The stability holds. Here are the Euler curves, exactly for the same data sets. And as you see, we do have this evidence that we are looking at the cycle. So somebody asked me, which simplicial complex construction have we used over here? Anybody knows? What is this? Have we used Vittorius-Rips or Czech or alpha complex construction? Okay, I mean, I got 3 answers. Well, okay, I mean, if you look north from this country, you realize the democracy. No. Stop. You give me an answer, I will ask why. Okay, think quietly. If you know the answer, tell me. So look, if you look right here, it's the moment when actually we have quite big balls already. Everything is connected. There are no more cycles. And yet we get a jump in Euler characteristics. The jump don't come from new connected components because, the balls are already large. It doesn't come from new cycle because everything is glued. It comes from a higher dimensional homology, which we won't get if we are looking at the check or Vietoris ribs. So that's one of the fake generators that's one of the fake generators you can get from Vietoris ribs, but we cannot get with check or alpha. So this when you get a very regular sample of points from a unit circle, they happen. This is what happened over here. So looking at the data, you can actually figure out how it was created and get another candy after dinner, after lunch. Okay. So let's see. We have 3 minutes and 13 seconds. So I will be able to kind of wrap up the Euler curves. Easy to compute, embarrassingly polar. So I don't think I mentioned it over here. So we did a comparison with Goody, and we have a prototype distributed implementation. So what do you really need to do over here is to construct your complex locally at the start of a vertex and do the counting of the simplices over there. And when you make sure that you don't double count, you can actually, put your point cloud in the certain collection of distributed servers that don't talk to each other, locally do the construction, do the sum, merge them, MapReduce type stuff, and get the Euler curve. So with a simple prototype Python implementation, we got like more than 2 orders of magnitude larger complexes compared to what you can do with Goody on this single memory unit. And we only get 2 orders of magnitude because it was pointless to get more, because you can easily cook up examples on which you can get as high as you wish for large enough data. So it's embarrassingly parallel. We have a prototype implementation. If you need it for large data, it's stable. And here we are coming to the multi-filtrations. So there is a problem, and I'm not discussing in details what is the problem with multi-persistence. Let's simply say that there is no obvious finite analog of a barcode for multi-filtrations. But what happened if I actually try to generalize this concept of the Euler curves to multi-filtrations? In order to answer this question in the next 1.5 minutes, that should be more than enough. Let's think what is an Euler characteristic curve. So an Euler characteristic curve, if I have a simplex that appears at the filtration value f of s, then this simplex contribute to Euler characteristic this Heaviside function, which is equal 0 before the filtration, and then it's equal 1. And then we need to multiply this function by -1 to the dimension of a simplex s. And once I may actually shut up and write it down. So once we take the sum over all simplices in our simplicial complex S, I take -1 to the power S, and I call it, let me call it, maybe that's not. If I call the CH of S this characteristic function of a simplex, which is 0 below its filtration value, and then became 1, then this is precisely the Euler characteristic curve of my simplicial complex S, right? Okay. What happens if this characteristic function is not a single number, but multifiltration? That is an analog of a step function for two critical multifiltration. So our simplex S, it appears on 2 incomparable values of in R2. And then the analog of the step function that we had over here is a function which is equal to 1 for every point which is greater to at least one of those, and 0 lexicographically greater to either one of those, and 0 otherwise. And then you just take this formula and substitute this characteristic function for one-dimensional filtration with something like this, for as many filtration parameters as you wish. And I call it Euler characteristic profile. We want to see this example before we go for lunch. So, a unit circle contaminated with noise, lower density noise. And what we have over here is the condensity. So it's 1 over density or 1 over distance to my, say, second nearest neighbor. So those guys, they have a large distance to the second nearest neighbors. Those guys in the high density region, they have low. Does it make sense? Everybody's tired and we're getting there. So that's the Euler profile for the clear case. And as you see that there's this brownish value of 0. An evidence for our circle. That's the Euler characteristic profile for the contaminated case. And again, we see a lot of brownish. Let me just show you the brownish thing. So we still see the signature of a circle quite easily visible in the case of multi-filtration. So I promise you a partial solution. There's a partial solution. Do you have any questions about partial solution? What are you? You're supposed to remind me something. Any questions about this partial solution? We'll be discussing it. Wait a second. The gentleman was first. Tell me. I mean, it depends how fixated you are on multidimensional persistence. It is a solution. It's not this solution. There is no this solution. It's a solution, right? Yes? Oh, sorry. So again? Sorry. Oh, yes, you can. I mean, yeah. So how? Okay, that's a good point. So, second, what's your name? Enrique is suggesting a simple procedure. Let's kick out those parts. But then you need to set up a threshold. Okay, I may say, okay, I don't like the points of condensity above 0.25. Pretty arbitrary threshold, right? And I may end up with a similar type of problem. You can eliminate, but you need to tell, okay, what is the minimal value of condensity that you accept? So there's a parameter. It's not a parameter free. Yes, and this is what people are doing. But you are introducing an artificial parameter into your analysis. And over here, we are not. It's parameter free. Okay? Any other questions? Yes. Well, that does it or does it not? I mean, at the end of the day, it tells you about the global topology, right? Euler-Poincare formula. It's locally computable, but the aggregation over here gives you a global information. We are not studying inclusion maps in homology. And that's why we are free from the problems of multidimensional persistence. That's the way. I mean, the only way is like Kobayashi Maru in Star Trek. The only way to win the game is to change the game. If you know what I mean. Any other questions? So are you tired enough to laugh at the joke? I'll try to make it slow. Any guesses? When do astronauts eat? Okay, let's go. Thank you very much.